For more than a century, physicists have been fascinated by dark openings, with the idea building up momentum around 1916. These inestimable irregularities are among the most enrapturing and mysterious peculiarities we know, sitting at the convergence of tremendous gravitational forces and a curious intangibility beyond our grasp. A dark opening, possibly gauging as much as 2 to 4 times the mass of our Sun, remains a puzzling presence in the universe. Notwithstanding many years of serious research, our comprehension has extended from practically no information to piecing together more subtleties, with significantly more disclosures being made as of late. A breakthrough by Michio Kaku has uncovered surprising insights about the interior of dark openings, which might challenge our long-held presumptions and propose new viewpoints on the nature of these divine bodies. This new data opens doors to deeper investigations into what might have been neglected until now. Join us as we venture further into the fascinating universe of dark openings and uncover what's concealed within the universe's vast and shifting secrets. However, what exactly are dark openings? Before we dive into the latest findings by Michio Kaku, it's essential to revisit the fundamental understanding of dark openings. While most of us have a general sense of what a dark opening is, there are still several key elements that remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of dark openings. At that time, the idea was purely theoretical. It was only about 50 years later that evidence confirming the existence of dark openings was found. This discovery came in the 1960s during investigations of the star X1, a brilliant celestial body emitting X-rays. Observations showed that these X-rays were not just randomly moving, but were being drawn into a dense, invisible mass. This mass, later identified as a dark opening, changed our perception of the universe. The discovery was astonishing, as it proved that dark openings were not just inventions of Einstein's imagination, but real cosmic phenomena that warranted further study. Following this pivotal discovery, researchers worldwide began a global mission to uncover more about dark openings. Their efforts led to the realization that the Milky Way alone might contain around 100 million dark openings. However, due to the challenges in detecting them, this estimate remains uncertain. Despite being incredibly difficult to pinpoint, scientists believe that many of these massive entities are hidden within our galaxy, making it even more crucial to understand them. The core concept, gravity. Dark openings exert such immense gravitational forces that anything entering their space is pulled into a singularity, a point where the laws of physics, as we know them, cease to function. Simply put, dark openings are like enormous vacuum cleaners, pulling everything into them. One of the most frightening aspects of dark openings is that if someone were to fall into one, they would gradually stretch out and become part of the singularity, their body torn apart by the extreme gravitational forces before reaching the point of complete obliteration. It's best to stay far away from them. However, dark openings are scattered across the universe, and despite the closest one being nearly 500 light-years away, their presence still raises real concerns. In 2021, scientists achieved a remarkable milestone by capturing the first clear image of a dark opening, M87. This accomplishment was the result of numerous nights spent taking photographs and aligning them to create a single, solid image. As more data was gathered, experts discovered that dark openings consist of 3 distinct layers. Contrary to the common misconception that they are just vast voids, these layers include 1. The event horizon. This marks the boundary beyond which nothing can escape. Once something crosses this threshold, it is inevitably drawn toward the dark opening. 2. The photon sphere, a region where light itself is trapped, unable to escape due to the powerful gravitational forces at play. 3. The singularity, a point where all matter is compressed into an infinitely small space, causing the very fabric of reality to collapse, and where known laws of physics break down. What's even more intriguing is that each dark opening is unique. While they follow the general 3-layer structure, their behavior can vary significantly, making them particularly challenging to study. Conventional scientific methods don't apply to the study of dark openings, forcing researchers to explore these anomalies through indirect means, such as observing the radiation they emit or analyzing the gas and dust swirling around them. Sending a probe directly into a dark opening is futile, as anything crossing the event horizon is inevitably pulled toward the singularity, where it is crushed into nothingness. This inescapable fate means billions of dollars cannot be spent on probes that would meet their end before providing any meaningful data. Thus, scientists are left to study dark openings in 2 dimensions, despite their 3-dimensional nature. Adding to the complexity of dark opening research is the fact that no 2 dark openings are identical. When studying them, we must account for the breakdown of physics as we understand it. Theories about the origins of dark openings suggest they may form when massive stars collapse in on themselves. As a star burns through its fuel, it can no longer generate enough energy to counteract the inward pull of gravity, eventually leading to its collapse into a dark opening. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. The role of NASA and new discoveries. To better understand dark openings, NASA scientists turn their attention to the center of the universe, particularly the M87 galaxy. There, they observed a powerful vortex of hydrogen gas spinning at astonishing speeds of 1.2 million miles per hour. The centrifugal force should have caused this gas to scatter, yet it remained intact, suggesting the presence of a massive object at its center, likely a dark opening. This object is believed to be up to 3 billion times the mass of our Sun. Another major theory was proposed in 1963 by a New Zealand mathematician Roy Kerr, who used Einstein's equations to describe the behavior of rotating dark openings. He argued that instead of collapsing into a point as previously thought, a rotating dark opening forms a thin, ring-like structure known as the ergosphere. This spinning ring of matter is crucial to understanding the breakdown of physical laws near dark openings. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through space-time, connecting distant parts of the universe or even parallel worlds. Wormholes and the quest for understanding. To grasp the concept of a wormhole, it's essential to understand space-time as described in Einstein's theory. Space-time is a 4-dimensional fabric that is warped by objects with mass. This warping creates gravitational fields that influence the movement of other objects. Think of space-time as a sheet of paper. If you fold the paper, you create a shortcut between 2 points. This shortcut is the essence of a wormhole, a passage through space-time that could connect distant locations almost instantly. Although wormholes remain theoretical with no direct evidence of their existence, they are a natural outcome. Physicists have long sought a theory of everything, a framework that unites Einstein's general relativity with quantum mechanics. While general relativity explains gravity and large-scale cosmic structures, quantum mechanics governs the behavior of particles at the smallest scales. The challenge is that these 2 fundamental theories do not align when applied to extreme environments, such as dark openings. One of the leading candidates for a unified theory is superstring theory. This theory suggests that all fundamental particles are, in fact, tiny vibrating strings, and the different vibrations determine their properties. If proven correct, superstring theory could provide answers to some of the deepest mysteries in physics, including the nature of dark openings and the existence of higher dimensions. However, verifying this theory remains an immense challenge. The extra dimensions proposed by superstring theory are believed to be so small that they are undetectable with current technology. Still, ongoing research in high-energy physics, such as experiments conducted at the Large Hadron Collider, LHC, continues to push the boundaries of our understanding. The role of quantum mechanics in dark openings. A major breakthrough in dark opening research came from Stephen Hawking, who introduced the concept of Hawking radiation in 1974. He proposed that dark openings are not entirely black, but emit radiation due to quantum effects near the event horizon. Over time, this radiation causes the dark opening to lose mass and eventually evaporate. Hawking's work suggested that information trapped inside a dark opening might not be lost forever, a concept that challenges the classical understanding of physics. This information paradox remains one of the biggest unresolved problems in modern physics. If a unified theory is ever developed, it must reconcile how quantum information behaves inside dark openings. The future of dark opening exploration. Despite the challenges, advancements in technology are allowing us to study dark openings in unprecedented detail. The Event Horizon Telescope, EHT, a network of radio telescopes across the globe, captured the first-ever image of a dark opening in the M87 galaxy in 2019. This achievement confirmed many of Einstein's predictions and provided visual evidence of a dark opening shadow. Future missions aim to study dark openings using space-based telescopes and gravitational wave detectors. The detection of gravitational waves by LIGO and Virgo has already provided new insights into how dark openings merge. By studying these ripples in space-time, scientists can learn more about the properties of dark openings and their role in the evolution of the universe. Could dark openings be gateways to other universes? Some theories suggest that dark openings might not just be cosmic vacuums but gateways to other universes. This idea, inspired by Einstein-Rosen bridges, wormholes, proposes that instead of leading to a singularity, a dark opening could connect to another region of space-time or even an entirely different universe. While purely speculative, this concept has fueled interest in multiverse theories, which propose that our universe is just one of many. If true, dark openings might hold the key to traveling between these parallel worlds. However, without experimental evidence, these ideas remain theoretical. Conclusion: the endless mystery of dark openings. Dark openings continue to challenge our understanding of physics, forcing scientists to rethink the nature of space, time, and reality itself. Whether they serve as cosmic destroyers, information vaults, or potential gateways to other realms, they remain one of the most fascinating and enigmatic phenomena in the universe. With ongoing advancements in observational astronomy, quantum physics, and theoretical research, we are inching closer to unraveling the secrets of dark openings. Perhaps in the near future, new discoveries will reshape our understanding of the cosmos, bringing us closer to a theory of everything, one that finally bridges the gap between gravity and quantum mechanics. Until then, dark openings remain a tantalizing mystery, inviting humanity to keep exploring the unknown depths of the universe. Indications of little vibrating strings. These strings can vibrate at various frequencies, with every vibration corresponding to a different particle. Similarly, just as a guitar string can produce different musical notes depending on how it vibrates, the fundamental particles of nature could correspond to different vibrational patterns of superstrings. If proven, this hypothesis wouldn't just provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the structure of the universe. This could potentially provide answers to some of the biggest questions in physics, including the nature of dark matter and dark energy, which together account for the majority of the universe's mass and energy, yet remain largely mysterious. Yet, despite its elegance and promise, superstring theory remains unproven. One of the major obstacles in testing the theory is that the extra dimensions it predicts are so minuscule that they are beyond our current observational capabilities. Detecting these dimensions would require instruments of extraordinary sensitivity and precision, and even then, the evidence might only be indirect. This makes superstring theory a particularly difficult subject to test through conventional scientific methods. However, its mathematical beauty and coherence make it one of the most compelling ideas in theoretical physics. At the same time, researchers are also working on alternative approaches that could lead to breakthroughs in our understanding of black holes. For instance, quantum gravity is another field of research that seeks to unify the principles of quantum mechanics, which govern the behavior of subatomic particles, with the theory of general relativity, which explains the behavior of massive objects like planets, stars, and black holes. The hope is that by combining these two theories, scientists can gain a clearer understanding of how gravity operates at the quantum level and, in turn, gain deeper insights into black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity is particularly crucial when studying black holes, especially near a black hole's event horizon, where gravity is extraordinarily intense. This region demands a theory that accounts for both quantum effects and relativistic effects. In fact, the interior of a black hole, where the singularity exists, is one of the most perplexing and extreme environments in the universe. The singularity represents a point where space and time become so distorted that the standard laws of physics break down. Understanding what happens in such a place requires a theory that can reconcile quantum mechanics and general relativity. This challenge has led to the development of ideas such as loop quantum gravity and other quantum gravity models, which aim to resolve these inconsistencies and provide a more complete picture of black holes. As we continue to explore the mysteries of black holes, one thing is certain: the more we learn, the more we realize how much there is still to discover. Black holes are not just points of destruction, but also places of immense complexity and potential. Whether they are gateways to other dimensions, as some theorists suggest, or hold the key to understanding the deepest secrets of space and time, black holes remain a crucial area of study. As our tools and theories advance, so too will our understanding of these enigmatic objects. Looking ahead, the next major challenge will be refining our methods for observing and studying black holes. One of the most exciting advancements in recent years has been the development of gravitational wave astronomy. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as merging black holes. By detecting and analyzing these waves, scientists can learn about the behavior of black holes and other celestial objects in ways that were previously impossible. The detection of gravitational waves has already provided groundbreaking insights into the dynamics of black hole mergers, and future experiments are likely to yield even more discoveries. In addition to gravitational waves, another promising area of research involves the use of advanced telescopes and imaging techniques. The Event Horizon Telescope, EHT, which produced the first-ever image of a black hole in the M87 galaxy, is an example of how innovative technology can shed new light on black holes. By combining data from multiple radio telescopes around the world, the EHT was able to capture an image of the black hole shadow, offering a glimpse into one of the universe's most mysterious phenomena. As technology continues to improve, it is likely that we will be able to observe black holes in even greater detail, revealing more about their structure, behavior, and role in the cosmos. The study of black holes is not just about understanding these strange objects in isolation. It is also about uncovering the fundamental workings of the universe. Black holes are central to our understanding of space-time, gravity, and the very nature of reality. By studying them, we are not only learning about these objects themselves, but also about the laws that govern the universe at its most extreme. Ultimately, the study of black holes is one of the most exciting and challenging fields in modern physics. With each new discovery, we move closer to unraveling the mysteries of these cosmic giants. Whether through the study of gravitational waves, advancements in imaging technology, or the development of new theories, black holes continue to captivate the imagination of both scientists and the public. As we explore the universe's most extreme and enigmatic objects, we are forced to confront fundamental questions about the nature of space, time, and existence itself. In doing so, we may be on the verge of unlocking some of the greatest secrets of the universe, perhaps even finding answers to questions that have eluded humanity for centuries.